In this video, we are going to study about rolling motion. When a body like sphere or wheel rolls on the surface, then that motion is called as rolling motion. But the rolling motion can be treated as the combination of both translational motion and rotational motion. As shown in this figure, we have considered a wheel which is performing rolling motion on a horizontal plane. Now you can see here this point C, which is the center of mass, and when rolling motion starts, then this center of mass is going to perform translational motion, whereas the particles other than center of mass are going to perform rotational motion. To understand this, let us consider a point A which is near to the circumference of this body, and when this rolling motion starts, then the motion of this particle which is present along this on the circumference of the circle is going to be somewhat like this. Therefore, the total kinetic energy of this rolling motion is equal to the combination of translational rotational. So it's a combination of translational kinetic energy plus rotational kinetic energy. Now we will derive expression for total kinetic energy of a rolling body. As you can see here, we have considered a wheel which is going to roll on this plane surface. Mass of this body is denoted by m, which is rolling on a horizontal surface. Now you can see omega, it is the angular speed of this body, and v is the linear speed of this body. Now we are going to consider, let capital I is the moment of inertia of this body. Therefore, total kinetic energy of this body, that is E, is equal to, it is a combination of translational and rotational kinetic energy. So we can write E suffix T means translational kinetic energy plus E suffix R, that is rotational kinetic energy. Therefore, total kinetic energy of a rolling body is nothing but the addition of translational and rotational kinetic energy. So first of all, we'll write for this translational kinetic energy, we can write E translation, that is nothing but half mv square, where m is the mass of the body and v, it is nothing but the translational speed of this body. And now for rotational kinetic energy of this body, ER, we can write this is nothing but half I omega square, where I is the moment of inertia of this body and omega is the angular speed of this body. Therefore, total kinetic energy of this rolling body E. Now we are going to substitute this translational kinetic energy and rotational kinetic energy in this equation. So we are going to get E translational, that is nothing but half mv square, plus E rotational, that is nothing but half I omega square. Now we know that, but this I, which is nothing but moment of inertia of the body, we can write this as mk square, where m, it is the mass of the body and k is the radius of gyration. And as well as we are also knowing the relation between linear speed and angular speed, that is nothing but v is equal to r omega v linear speed, r radius, omega angular speed. Now we are going to substitute this value in this above equation. Therefore we are going to get total kinetic energy of rolling body E is equal to half m. For v, we can write this is r square omega square. For this v, we have substituted this r omega plus this half. For this I, we can write this is nothing but m k square omega square. Therefore, we are going to get E is equal to half m omega square. We can take out common into bracket. So this is nothing but only r square plus k square. Therefore, we can write E is equal to half m. For omega, we can write v by r. So this becomes v square upon r square into bracket r square plus k square. Therefore, E is equal to half, this is mv square into bracket, this r will shift it inside this, so we are going to get 1 plus k square upon r square. So this is the equation for total kinetic energy of a rolling body, where m is the mass of the body, v is the translational speed of the body, K, it is the radius of gyration of the body, and R, it is the radius of the spherical body. This is rolling motion of a body on inclined plane, which is the combination of translational motion and rotational motion. Now we are going to discuss rolling motion of a body on an inclined plane without slipping, that is pure rolling motion. For this, here we have considered a rigid body of mass say capital M and radius capital R rolling down on an inclined plane of angle of inclination theta, and the body is present at height h. Now this body is going to be start from rest, so we have written u is equal to 0. So at height h, this body must be possessing some potential energy, and when this body rolls down, then that potential energy get converted into kinetic energy. Therefore, we can write potential energy of this body at this highest point must be equal to kinetic energy of this body at this lowest point. Now for potential energy, therefore we can write this nothing but mgh is equal to kinetic energy. Now kinetic energy, we are talking about kinetic energy of a rolling body, and we know formula for this, which is given by half mv square into bracket 1 plus k square by r square, where m mass of the body, v linear speed, k radius of gyration, r is the radius of the body. Therefore this m will get cancelled with this m, therefore we will get v square is equal to 2gh upon 1 plus k square upon r square. Therefore we will get v is equal to under root 2gh upon 1 plus k square upon r square. This equation gives us the velocity of this body when it will reach at the lowest point. Now let us find linear acceleration of body while rolling down on inclined plane. For this we are going to make use of third kinematical equation, which is v square is equal to u square plus 2as. Now here we can see the initial velocity, that is u is equal to 0. Therefore we can write v square is equal to 2as. Therefore we can write a is equal to v square upon 2s. But we already obtained the expression for velocity of the rolling body and is given by, but v is equal to, we know this, under root 2gh upon 1 plus k square upon r square. So we will substitute this value of v in this equation. Therefore we will get a is equal to, we can write this equation as 2gh upon 1 plus k square by r square. Here v square, this square root goes, and we can write it directly into, in the denominator we have this 2s, 1 upon 2s, where s, this is the displacement of this body. But from this figure we can see sine theta opposite side, that is h, upon hypotenuse, that is s. So from this we can write it as s is equal to, this implies s is equal to h upon sine theta. So we'll substitute the value of this s in this equation. Therefore we are going to get acceleration a is equal to 2gh upon 1 plus k square by r square into 1 upon this 2 as it is, and for this s we can substitute this value, which is nothing but h upon sine theta. Therefore by solving this we are going to get a is equal to g sine theta upon 1 plus k square upon r square. This is the equation for acceleration of a body rolling down the plane. Thus in case of pure rolling motion, velocity of the body is given by v is equal to root 2gh upon 1 plus k square by r square, and acceleration is given by a is equal to g sine theta upon 1 plus k square by r square. Whereas in case of pure sliding, that is without friction, velocity is given by v is equal to root 2gh and acceleration is given by a is equal to g sine theta. We can clearly see in case of purely rolling motion and in purely sliding without friction, this factor 1 plus k square by r square in velocity and in acceleration is going to be more effective. Now let us discuss velocity and acceleration in case of rolling motion of different shapes. Here we are going to consider different shapes, that is ring, disc and solid sphere, which are going to be rolled down over this inclined plane, which is inclined at an angle theta. And in this case, what is going to be velocity and acceleration of ring, disc and solid sphere, that we are going to discuss. In this table, as you can see, we have considered three shapes, that is ring, disc and solid sphere, in front of which we have written their respective moment of inertia, and in the next column we have obtained their radius of gyration. Now by substituting the value of radius of gyration in the formula for velocity and acceleration, we have got the different velocities of different shapes as well as their values of acceleration. If you look at the velocity column, we can see the velocity for ring, that is root gh, which is minimum, and velocity for solid sphere, which is root 10 by 7 gh, is maximum. Whereas if you look at the radius of gyration column, you can see radius of gyration for ring, it is r, which is maximum, whereas for solid sphere it is r root 2 by 5, which is minimum. From this we can conclude that more is the value of radius of gyration, small is the value of velocity. As you can see here, we have considered a ring and a disc. Both are approximately of the same mass and radius, and we are going to roll them down simultaneously. But according to our previous discussion, radius of gyration of the ring is more as compared to the disc. Therefore, velocity of the disc is going to be greater than the velocity of the ring. Therefore, disc will reach to the bottom first as compared to the ring. Now here we have considered all the three shapes, that is sphere, disc and ring, which are going to be rolled down over the inclined plane. Radius of gyration or moment of inertia of the ring is maximum, and that of for sphere it is minimum. That is, distribution of mass about given axis of rotation in case of ring is more as compared to sphere. Therefore, velocity of the sphere is greater as compared to the velocity of the ring, and due to this, sphere will win the race.